Assalamualaikum warahmatullahi wabarakatuh. We are from group 5 that will present about the SCHOTTKY diode. First of all, I am going to introduce our group members that consist of 4 persons, which is SYAFIQ, SYAZWAN, HIDAYYAH and AIMAN. Next, I will talk about basic structure of SCHOTTKY diode. A metal semiconductor junction is used in order to create SCHOTTKY diode. There is no depletion layer in a SCHOTTKY diode because of SCHOTTKY diode have silicon that has been doped on one side and a metal compound on the other side of the junction. SCHOTTKY diode are unipolar devices as opposed to ordinary PN junction diode which are bipolar.
Hi, so now I will explain about characteristics of Schottky diodes. First, Schottky diodes is formed by a metal semiconductor junction, which is typically using a metal such as platinum or aluminium on a semiconductor like silicon. Second, Schottky diodes have a low forward voltage drop in because this diode has a much higher current density than an ordinary of PN junction. Third, Schottky diode have a fast switching speed, which they can switch between conducting and conducting state quickly. Fourth, Schottky diode have a low reverse recovery time. This refers to the time it takes for diode to switch from the conducting to non-conducting. Next, Schottky diode have a lower breakdown voltage compared to PN junction diodes. It's shown that Schottky diode are not suitable for high voltage application where high reverse voltage tolerance is required. So, the lastly of characteristic of Schottky diode is it can operate effectively over a wide temperature range, which making them suitable for use in application that require operation in high temperature condition.
Now let us move to the working principle of Schottky diode. First is barrier formation. When the metal and the semiconductor material come into contact, a metal semiconductor junction is formed. Due to the difference in work function between the metal and the semiconductor, a potential barrier is created at the junction. This barrier prevents the flow of electrons from the metal to the semiconductor. Forward bias. When a forward bias voltage is applied to the Schottky diode, the potential barrier is reduced. This reduction in barrier height allows electrons to flow easily from the metal into the semiconductor. Next is current flow. As the forward bias voltage is increased, the number of electrons crossing the metal semiconductor junction also increases. This results in a current flow through the diode. The absence of the depletion region in the Schottky diode enables fast switching and low forward voltage drop compared to the regular diodes. Lastly, reverse bias. When the reverse bias voltage is applied, the potential barrier is increased, making it even harder for electrons to flow across the junction. As a result, very little current flows through the diode in the reverse direction.
For simulation, I use multi-sim application to get the IV characteristic of SCHOTTKY diode. The component that we use in the circuit is voltage source, a resistor, an IV analyzer, and the last one is SCHOTTKY diode. And this is the graph that we obtained from the circuit by using the IV analyzer.
Assalamualaikum and hi, my name is SYAZWAN. I want to continue the presentation with the discussion of the simulation from the SYAFIQ AIMAN. For the discussion, the simulation and result, we can see the same like the IV characteristic for the diode, but for the usage of SCHOTTKY diode is more specific than the other diodes. First, I want to talk about forward bias in the graph. In this region, the diode is connected in such a way that the positive terminal of the voltage source is connected to the P-type region of the diode and the negative terminal to the N-type region. Initially, as the voltage increase, the current remains very low until it reaches a certain threshold known as the forward voltage drop. Once the forward voltage exceeds this threshold, the current starts to increase rapidly. The IV characteristic curve in this region is relatively steep. For the second, about the reverse bias breakdown. As the reverse voltage or opposite polarity across the diode increase, there is a point called the reverse breakdown voltage, where the diodes break down and allows current to flow in the reverse direction. This region is characterized by a sudden increase in current while the voltage remains relatively constant. This breakdown can be either Zener breakdown or avalanche breakdown, depending on the type of the diode. Third is about the reverse bias, or we call reverse current. Beyond the breakdown voltage, the diode is in a reverse bias and the current increase significantly. However, the increase is not as steep as during the breakdown. This region is typically represented by a gradually sloping curve on the IV characteristic graph. And finally, for the reverse bias, or we call leakage current. In this region, the reverse voltage continues to increase, but the current remains relatively low. This leakage current is very small and almost constant. The IV characteristic curve becomes almost flat in this region. I want to tell about application of the SCHOTTKY diode. For the first of application, SCHOTTKY diode is a power rectification. SCHOTTKY diodes are frequently used in power supply circuits for the rectification. When compared to ordinary diodes, which have higher voltage drops, their low forward voltage drop voltage for SCHOTTKY diode is active usually around 0.3 until 0.5 volt, enable for more effective conversion of alternating current AC to change to direct current DC. They are especially useful in switching power supplies, voltage clamping circuits, and DC-DC converters. For the second, SCHOTTKY diodes are often used as fast switching device in digital circuits, high-speed data transmission system, and telecommunications equipment. Their lower forward voltage drop and minimal recovery time make them suitable for high-frequency switching applications. And lastly, for the application of the SCHOTTKY diode is voltage clamping. SCHOTTKY diodes are used as voltage clamps in digital circuits to limit voltage swings and protect sensitive components from overvoltage conditions. They can prevent logic gates and other digital components from being damaged by excessive voltage levels.
Throughout our academic journey in the field of electronics and semiconductor devices, we have come across numerous concepts and devices that have expanded our knowledge and understanding. One of its primary advantages is significantly reduced forward voltage drop compared to regular diodes, resulting in lower power losses. This feature makes the SCHOTTKY diode ideal for applications that require high-speed switching or low power dissipation. Furthermore, its fast switching capability and minimal reverse recovery time contribute to improved efficiency in high-frequency circuits.
Another notable characteristic of SCHOTTKY diodes is its lower junction capacitance, which allow for faster signal transition and better high-frequency performance. This quality has implications for applications such as radio frequency circuit, mixers, and detectors. Moreover, this experience has taught us the importance of exploring alternative solutions and understanding the trade-off associated with different devices. In conclusion, studying SCHOTTKY diode has been a rewarding experience, and it has broadened our understanding of semiconductor devices and their diverse applications.